Hi, gang. Math 5500, brief, and I mean really, really, really brief on calculating and interpreting confidence intervals for the slope and the intercept. Some of the easiest stuff we'll do, but of course, if you don't know the R command, it's not easy, is it? And just touching on this because we dive into the weeds on this. I believe it's lesson three or four. We dive into the weeds quite a bit. But anyway, just to get our feet wet. If I want to calculate, let me pump the brakes a little bit. Let's say that we want to predict body fat from triceps, and and I want to calculate the 95% confidence interval for the slope and the intercept. So the very first thing I'd want to do, well, I'd need to do, is just create the model. And I really don't even need to look at it, but I'm going to. So what I can see is I can see that the estimate for the intercept is about 1.5, and the estimate for the tricep is about 0.86. All right, so I want to build margin of error around this. Now the reason I do is this estimate, I'm not really sure how many subjects we have here. Let's just do the length and see what happens. So we have 20 subjects that have provided measurements for this data set. But and if I'm interested in just discussing the measurements for these 20 subjects, then I just look at the mean and the median and standard deviation and correlation. But, huge but, if I want to generalize from these 20 people to the larger population of relations of triceps and thighs and body arms and body fat, again to everyone, then I get into what we call, inference and p-values and confidence intervals. So, because this 0.857 is specific to these 20 subjects, I understand that the sampling distribution of my beta 1 is going to contain variation. In other words, if I go in and take a random sample of 20 more subjects and measure their tricep, thigh, mid-arm, body fat, and so on, and I calculate the estimate for the slope and the intercept for them, it's going to be different. It's going to have natural variation. So the confidence interval allows us to build margin for error around our estimate to account for that natural variation that we expect from sample to sample. Now, and again, one of the lessons is inference for regression and ANOVA, and we dive into the weeds a lot deeper there. But let me just demonstrate it. So I have my model, and to get the confidence interval, it's easy. Just do confidence interval model. So this tells me, okay, first of all, the default is the 95% confidence interval. If I do want to change that, all I have to do is add the, I forget what it is, I believe it's a level point. Let's say we wanted a 90% confidence interval instead. We just do level equal 0.90. And you can see with a 0.90, the width of the interval isn't as wide as with the 0.95. Well, it's a give and take, right? The more confidence you have that your interval contains the population intercept or the tricept or any measurement, it's just going to be wider. For example, I don't know the ages of any of you in this class, but I am 100% confident that the average age of all 26 of you, or 28, whatever it is now, is somewhere between 0 and 100. Right? Okay, I say, yeah, Dr. Darbro, totally brilliant. But seriously, I have gone so ridiculously wide with my interval, 0 to 100, that I can express a large amount of confidence, 100%. But what if I say, okay, I've got a confidence from from maybe 24 to 26. I don't know how confident I am. I would express less confidence there. Well, it works the same way with calculating a confidence interval. The wider the margin, the more confidence I have. So to interpret, let's just concentrate on this line right here. Let's concentrate on what does that tell me. I would say that, again, it's calculated 95%. This 2.5%, if you think about the sampling distribution, you have 95% in the middle. Well, to the left of that and to the right of that, you've got 5%. Well, because that 5% has to be distributed equally, because of symmetry, you have 2.5% in the tail, left tail, and 2.5% in the right tail. So I have the lower bound has 2.5% below it. The upper tail has 97.5% below it because it has that 2.5% above it. All right. So again, my interpretation, I would say there is a 0.95 probability that this interval, so we're looking at what, 0.587 to 1.128 contains the population slope. So there's a 0.95 probability that this interval, 0.587 to 1.128, contains the population slope. Similarly, it's hard to say when you've only had half a cup of coffee. Just going around to two places here because I want to. All right. Now, one thing to notice that this interval contains 0. When the interval contains 0, we can't distinguish between the population intercept being 0 and not 0. So in that case, we will never have statistical significance if this interval contains 0. Same thing with the population slope. If that interval contains 0, we will not have statistical significance. And again, if been a while since you've had a stats class, and maybe you've only had an intro stats class, don't sweat it. If that just went completely over your head, pump the brakes. Just trust the process. We dive into the inference for regression in a later lesson. So I really can't think of anything else that I wanted to demonstrate here. We get into prediction intervals and of the mean and get into a lot of things later, but I just want to keep this simple. All right. Take care, guys.